Good. And screen one. Let's take a look at the syllabus first, so we know where we are. We had last Wednesday, we had our exam. Today, we are going to continue with alternating current. Remember that when we were dealing with circuits, we cover both DC and AC circuits. But it was just one special type of AC circuit, okay, which was the resistor. So today we're going to revisit the AC circuit with a resistor, and I'm going to show you two more other types of AC circuits. Okay, side by side. Today here, let's go. That's my notes. 24th, 23. Okay, week number. What week number is this one here? Week number 12. Week number 12. And the chapter is chapter 22. It's not 22, chapter 23, alternating current circuits. Chapter. Okay, chapter 23. Let's take a look here. Here you go. AC circuit, alternating current circuits.
Professor?
Oh, yes.
I was actually talking to some of the students, and it seems like the majority of us didn't do well in the last exam. So we were wondering if there is a way that you could possibly, towards the end of the semester, drop our lowest score, or maybe if you can just give us some extra credit to add up to this exam, because it was pretty intense.
Okay, so here you go. Yeah, as you recall, I do drop the lowest exam of the partial exams, okay? So let's see, where is it written here? Thank you for pointing that out. And final partial exams. There will be 3 partial exams during the semester, each of them 2 hours long. We should expect one partial exam every 5 weeks. I'll drop the lowest grade of these exams and take the average of the remaining 2. Okay, so let's just you know, italicize and boldface it. Okay.
I have a quick question just to kind of piggyback off of that.
Yeah.
Well, I suppose 2 things. Do you think, like, could we spend some more time to prepare for the next exam just because this one was so intense? And also, too, if you would consider the extra credit option, because, you know, I know that you go over your notes thoroughly to set us up for success, but I mean, just looking back on the score, a lot of us were struggling pretty hard. Like, I believe no one got over 20. I believe 25.5 was the highest out of 35.5. So to just posit that to you to help the class.
Okay, so let's see. I was looking at the exams, you know, at the grades of the exam. The first, not just the second exam, but the first exam too, okay? The first exam, you know, most of you did very well. No, I was seeing like 80%, 90%, things like that, right? This exam, it was a lower grade, yes, it was a lower grade indeed. But remember that, you know, if you recall here, my A, B, C, and D's, you know, they're pretty, yeah, here you go. They're pretty liberal, you know. I'm aware that some professors set their B's at, their C's at 75. So So the exams are adjusted to ensure that you all, you all succeed, no matter how difficult they are. Okay. And I hope that answer regarding the third exam, right? You mentioned the third exam. Let's take a look at the third exam here. The third exam is scheduled for 17th of May. Okay. We cannot schedule for the Wednesday because it's a holiday, right? The Monday, we might be able to schedule for Monday if you want, but remember, it's going to be 1 week away from no, even less than a week away from the final. Okay, so you have to think whether you really want this exam on this Monday or maybe this Monday. Okay. We could do that this Monday here. Think about that. Okay, ideally, it should be here, but it's going to be a holiday, a Memorial Day holiday. We can also make it here, but notice that will be only 2 days away, right, from the final. So you have to think whether you want to have two exams only 2 days away from each other. Okay, think about that, whether you want to do it on Monday, right? And then we do the lecture on Wednesday. Yeah, we could do that on Monday if you don't mind. Okay, but there's not much I can do about the date, right? The date of the third exam.
Right, of course.
Okay.
But, what do you think about the possible extra credit option?
Since I'm dropping one of the lowest grades of the 3 exams, I already consider that an extra credit.
Okay, I just figured, just because the class was talking about this and we're all, doing the best that we can with, where we're at to get the best grade that we can.
Yeah. Yeah, the second exam was definitely, for what I saw in the grade, was more difficult, but that doesn't mean that everybody failed. Okay. It doesn't mean that everybody got a D or F in that exam, in the second exam.
But it did hurt our grade, Professor, big time. It lowered our grade in the class.
Mm-hmm. Oh, you have an opportunity for the third exam, right?
Correct, but that's why we were just wondering maybe the extra credit thing could be possible, just so it would give us a boost.
Mm-hmm. Okay, let me think about that. What type of extra credit that would be? Okay, and so you can get even better grades.
Thank you, Professor. I know we all really, really do appreciate this.
Okay.
Absolutely, thank you.
Okay. Let's see. Okay, let's go back to our notes. And here you go. That's the chapter, alternating circuit. Go. That's the chapter on the book. Nature of. No, that's one here. Here you go. That's capacitor and capacitive reactance. So let's just summarize, right? 2 types of circuits. Okay, 2 types of circuits. 2 types of circuits. DC circuits, the easiest one to understand. Current, let's put here like that, organized this way. Here you go. Current flows in a single direction. And then we have the AC circuits. Current flows in both directions. Okay. Source. What's the source here for the DC circuit? I'm gonna put it this way here. Source, battery. Okay. Source of an AC circuit. is a different type of device. Power source, right? Let's put here power source. Power source. Consider that as though it's the engine of the circuit. Power source that is going to be the generator that we discussed. Okay, generators use the electric induction phenomenon. Okay. So we can put this as a table. It's always good to organize it as a table. Insert. You know, we have here DC, AC, power source, current flow. And then we can DC, AC. Okay, we can put it here. Current flow, direction of current, and power source. That's cool. There are 3 students there. Power source. DC. Just one direction. It should be either clockwise or counterclockwise, right? Either one. One direction. Clockwise or counterclockwise. Both directions. Current keep on inverting direction. Sometimes it goes in one direction, sometimes it goes in the other direction. The power source here is the battery. And here's a generator, right? Remember how the generator works. We covered that in detail. The generator is the inverse of a electric motor. If you understand the electric motor, it's going to be easy for you to understand the generator. Okay. Types of AC circuits. We're going to study 4 types of AC circuit. One with a resistor only, with a capacitor only, with an inductor only. What is an inductor? You know, inductor is a solenoid, for instance, one type of inductor. It's one type of inductor. And we have a combination of the above elements. Can be RC, a resistor only, we denoted by R. Capacitor only, we denoted by C. Inductor, we denoted by L, okay? And we can have a combination of all those devices, RC, RL, CL, and L and R, LC. So we can have, let's see, circuits containing this RLC. Yeah, they don't have this notation. Oh, RCL. They call it RCL. Okay, RCL. other books called LRC. They all behaved in a different way. All those circuits behave in a different way. Of course, this one is more difficult to understand than the other ones. This one is the easiest one. Those two, have the same level of difficulty. And then, here we have a level of difficulty, even higher level of difficulty. Okay, we are going to start with the AC circuit with a resistor. And we already started doing that. We already did that before, right? And how does the power behave, right? You go here, power source behavior. I want to put another power source behavior. The voltage is constant. Oops. Voltage constant. Okay, in this case, remember how this generator works. It's like a sinusoidal voltage, very sinusoidally. Like that. Can be 9 volts, but here varies as time goes by. Let's see if I have an illustration for you of an AC circuit simulation. An AC circuit, right? Simulation, AC circuit. Okay. AC circuit simulation. We want the other one. Simple is here we go. Simple AC circuit. Let's see if this one is Walter. Let's see. Let's get this guy going. No, it's not this guy. Start. Okay. Well, it's not exactly what I want to show you, but here we have a generator. Okay, and the current. How does the current flows here? The current flows back and forth. You can see here. Here's my ammeter. Here's my voltmeter. See that. Oh, and look at the arrow of the current. Sometimes pointing to the right, sometimes it's pointing to the left. The generator does that. Okay, and here's the variation of the voltage. Here's the variation of the current. But this is an AC circuit with a resistor. That's what this guy here means. It's the resistor, okay? If we change to a capacitor, it's going to be a little bit different. See here how those sine waves look like in this specific circuit. And what you see here in here you go, it's V versus T and I versus T, right? V is in blue, I is in red. V is in blue, I is red. Here too, here's another way of representing the current and the voltage. Just a different way of, I'm going to talk about, this is called a phasor diagram. That's a new concept that I'm going to introduce to you. Okay, see that the voltage tags along with the current in the circuit. They are always, we say that they are always in phase. What does it mean being always in phase? That whenever the voltage is 0, the current is also 0. Whenever the voltage peaks, the current also peaks. 0 and 0, lower and lower. See, they are in phase. Okay, that's what we say the circuit being in phase. That's one example. Let me check another another circuit here. If the other one is Colorado, right? Colorado. Fat. Oh, it's fat. Okay, fat, right? Fat simulation. That's what we want. Let's see if they have an AC circuit there. No, that's lobsters. That's not what I want. I want this one here. The code that's gonna give you. I'm gonna post this address again in the notes. Secret, physics. The University of Colorado. Yep. And the University, oops. Colorado. Like that. And we call that is going to be very helpful if you keep on, very helpful for you to keep on referring to this site and look at the simulation that they have there. It's very, educational to look at those simulations. Now let's see, electricity, magnets, and circuits. I don't want. Let's see if they have AC circuits here. Let's take a look at this one. Yeah, looks like they have here. Yeah, they do have it. CRLC circuits, AC circuits. Now. Okay, there's a battery. Let's take a look at this one here. Why is that they don't let me run the scene? Oh yeah, here you go. Here is the generator. For some reason, he doesn't let me in. Let's see. Maybe he's here. Let's try that. Yeah, that's the one. Okay, AC. Good. We got it. Let me see if I have my generator here. Oh yeah, AC voltage. It's my battery. This guy is a battery that changes voltage as time goes by, and that happens with a given frequency. The frequency that we have here display in most countries is going to be 60 hertz. I'm going to get my switch. Here you go, switch right here. And a resistor. All right. Recall how the current flows in a DC circuit, right? The current flow in a DC circuit is just one direction. Let's see if I can put that here. I'm going to put it side by side. Hopefully I can. So you can compare those two. You'll see, yeah, I have a battery here. I'm going to make it smaller. So we can have everything in the same drawing. See, put it here aside. Okay, and move a little bit shorter. And let's take a look at the C circuit. I'm going to put my switch here as well. My resistor. Okay. Side by side. Okay, now look at those electric charges, right? That's the DC circuit. Battery, that's the generator. If I close, this circuit, the electric charges flows in the single direction, either clockwise or counterclockwise. In this case, this clockwise. I remember I have almost the same devices here, right? I have a resistor. I have a switch, and then wires. The only difference here is the power source. Now, if we close this circuit, look at how the electric charges move. They oscillate back and forth. They move in both directions. Okay, let's see if I can. Yeah, I can increase the frequency. And I cannot, unfortunately, I cannot increase the voltage. Oh, yeah. The voltage, let me check. Oh, yeah, I can increase the voltage. Okay, now that I increase the voltage, the amplitude of oscillation is larger. That's how the electric charges flow in an AC circuit. And again, what you see here is a generator. Okay, if I change the frequency, it's possible to change frequencies of this type of circuit. You know, they're going to oscillate faster. Okay. Now let me open here. I'm gonna open here. If we need, we can come back to that. Okay. So types of AC circuits with a resistor only. So what did I cover? AC circuit with a resistor only. Need to get the equation here. Okay, the voltage. And I'm going to come up with the book's notation. Capacitors and yeah, V naught. He's using V naught. I'm going to use V naught as well. V equal to V naught time what is he using as the notation 2 pi ft. Okay, 2 pi ft. F stands for frequency. Another way of writing this equation here is writing down omega here. Okay, 2 pi f is equal to omega, which is called, f is the frequency, omega is the angular frequency. F is the frequency, is called frequency of the circuit, number of oscillations per unit of time, omega is the angular frequency. And what means angular frequency? Radians per unit of time. 2 pi radians means 1 full oscillation. Okay. 2 different ways of writing the same thing. And I gotta erase that. What else we have to? Okay, and then we use using Ohm's law. Using Ohm's law, we can obtain the variation. We can obtain an equation for the current. Okay, V equal to Ri. Okay, V is V naught 2 pi ft, right? And we put Ri on the right side. And we get this relationship for the current. This is straightforward for the resistor. Note, see that both the current and the voltage, they have exactly the same argument in the sign. Okay, exactly the same. That's why we say that because both the voltage and current have the same argument inside the sign function, we say that they are in phase with each other. That we saw before. Okay. Then there is one more relationship that we can extract here. Many multimeters measure what we call the root mean square ratio, right? RMS, both for the voltage and for the current. So we have this relationship as well. Voltage RMS and current RMS. I'm going to put the voltage as well here. Like that. Side by side, they're side by side. I'm going to start to make a table as well. Here you go. Insert, that's going to be 1, 2, 3, 4, 1. Okay. R, C, L. voltage. And that's going to be current. And we're going to compare each of those circuits, the voltage. Here's the power source. And I'm going to, and what else? I'm gonna put here phase difference. Phase difference between the voltage and current, we say that's 0. They are in phase. And then you can plot that in a graph, okay? I did plot, I can do that, in Excel, but you can also, okay, right in here. You want to resume. Okay, so that's how the current and the voltage behaves. One representation, V versus T, and a second representation. This is a new one for you, but it's not difficult to learn. This one you're already familiar with because you went through math, you learned trigonometry, okay? Let's take a look at this phasor representation. Okay. You can represent the current and the voltage in 2 different ways. One, as a V versus T, or I versus T graph, or 2, as a phasor diagram. Okay. So let's see how the phasor diagram looks like. Go. This one. Okay. So here you go. And this is an unfortunate notation here. I'm going to do according to the book. Okay. So here goes. Yeah, here you go. 3 different circuits that we're going to look at. We're going to look at this circuit with a resistance, AC circuit with a capacitor, AC circuit with an inductor, okay? And we're concentrating on the first one. That's easier. Did I write it down here? Yeah, I wrote that down here. The easiest one is this circuit with the resistor, and I'm going to adjust my notation here. So it is the same notation of the book. Okay, 2 pi. Oh no, pi. Yeah. Symbol. Oh, didn't do that. Symbol. Huh. What a shame. Font. Let's try it again. It doesn't have it, that's why. It's here. Yeah. Let's see instead. Yeah. Here you go. Now oh, we still didn't do it. Oh man. Let's see. Nope. Okay, I will have to get that from my notes. So don't struggle with it. Yeah. I'll do that here as well. one more. All those three different circuits have the same power source resistor. I will replace here. And now let's take a look at this guy. I'm going to rename that. It's going to be V0. A phasor diagram is a vectorial diagram that moves in space, that moves in the XY axis. Okay. So you have this vector here that's representing the total voltage, the amplitude V0, the amplitude V0 of your circuit. Okay. And you have this angular velocity of rotation, that's omega t pi f. I'm going to put that f. And one more student coming in. By ft. And what does this phasor does? This phasor diagram does. You know, the component along the y-axis represents what? Represents the voltage at that specific instant of time. Okay, can you picture that? And this voltage changes as time goes by, or the phasor diagram keep on rotating. So if this guy here is the V0, it's a very useful and convenient notation, by the way. It simplifies a lot the mass. And I'm going to even put a different color. I'm going to put like a blue. Okay. As this phasor changes, oops, let's see. As I'm going to rotate this phasor, right? As this phasor changes, size and position, height, position, position. I have rotation here. Okay. I want to go the other direction. As this vector phasor rotates, the voltage also changes, right? That's how you should interpret this graph. Instead of using V0 sine of omega t, you just visualize something else. You just visualize this arrow of constant length rotating in a counterclockwise direction. And the projection of this arrow on the y-axis is going to be the actual voltage that you see. Okay, I'm gonna go back to what I had before. Oh, yeah, here you go, like that. This omega t shows the direction of rotation of the phasor. Because the current has exactly the same phase as the voltage, it's also represented by something like that. And I'm going to change the color here so it doesn't get mixed up with the color of the current. See Janet. 136. The current. Okay, the current has exactly the same phase in the case of the voltage. And did I put I naught here? Oh yeah, I can put I naught here as well. V naught over R can be written as I naught. Okay, IR. And if IRMS is equal to that, I naught is also equal to that. Here is the next phasor diagram illustrating both the phasor voltage and phasor current having the same phase lined up with each other. If I were to animate that, all those two would rotate together in the same direction. Okay, phase 0. So that's what you want to know, what you need to know about this first simpler circuit. Now, if you go to the capacitor, things start to become a little bit more different and interesting as well. Okay, whether it's for the capacitor or the inductor, the power source has exactly the same voltage there. Okay, that's going to be my next slide. Capacitor, right in here. So visualize that, you have the current bouncing back and forth. Sometimes the capacitor is fully charged, like is showed here. Sometimes it's partially charged. Sometimes this has no charge whatsoever, and other times has the polarity inverted. If we go to our FET circuit here, I'm going to remove this device, and I'm going to place a capacitor here. Let's see that we have a capacitor. Oh, it doesn't look like it has a capacitor. Yeah, that's unfortunate. Let's see here. That said, oh, we have a capacitor here. No, it doesn't have a capacitor here. Let's see if he can simulate a capacitor. Ideally, he should have a capacitor here, but he doesn't. Let's see, this one goes here. Okay. It's not gonna help. Show currents. Yeah, it really doesn't have it. Let's go. Okay, let's see how this guy plays here. We managed to do that before, right? Stopwatch. Let's go here. Let's put the resistor back there and see what's going on. Yeah, okay. Yeah. Okay, this guy, we don't have a capacitor here, so I cannot simulate a capacitor, okay? But basically, what do you have? You're going to have something like that. Let me do the simulation for you in my PowerPoint. Okay, at a given instant of time, you have loss of charges there in your capacitor. A little bit later on, the charges decrease. Okay. The charges keep on decreasing. Until it becomes 0. That's how you should see this animation, okay? You go 0, right? And then what was negative gets switched to positive. So this guy here that was negative now is going to become positive. Okay, in this specific case, the generator also changes polarity. And then you can get this one here. This one here is, don't forget, this one here is going to be inverted, right? It's already inverted. They're both inverted. 0, 1, 2. That's the 2 we have here. Oh, we already have that. Yeah, I already have that. Let's go for the next one. And so on, right? In this case, okay, in this case, the current inverted. Let's see if I can do that. Yeah, I got to invert the current here elsewhere. Here you go. Negative to positive, right? Which was counterclockwise, now it's clockwise. And here we do not have any current whatsoever. And by the way, this one here, I can put 0 as well, because it's about to invert the direction. Okay. And so on, right? So let's play the movie. It's gonna be something like that, you know? You gotta visualize those charges moving here in this circuit. Sometimes they're faster, sometimes they're slower. You know, at this very moment, they are almost came to a standstill because it got the largest charge, and then it start to decrease the number of charges in this very moment, okay? Decreasing the number of charge, okay, until it becomes 0, and then change direction. Building up the charges, okay? So let's go back to our notes. Okay, you can represent. AC circuit. Now I'm going to copy this one and paste in there. It's not exactly the same, okay? It's something, and the AC circuit with a capacitor only. The voltage is still the same, okay? Remember 2 pi f is omega, the angular frequency. But now is the capacitor, the situation is a little bit different. The current, remember that there is a relationship for the capacitor, right? The relationship for the capacitor is what? C equal to Q divided by V. That's what the relationship of the capacitor is all about. It doesn't, for the capacitor, Ohm's law doesn't apply. For the capacitor, Ohm's law does not apply. Ohm's law applies to, right, to the resistor. Okay, because of that, the current is going to have a different phase compared to the voltage. We can derive that, but only using calculus, okay? So that you have to memorize to, you know, to determine this relation mathematically, okay, you must use calculus. For this reason, you must memorize the results. Since this is not a calculus-based course, you have to memorize this result. You must memorize this result, okay? Instead of I equal to V naught over R sine of theta, you're going to have I equal to something else that I called a capacitive reactance. Okay, let's see. I'm gonna do that and see which. No. No, it's not the symbol. Let's see which symbol that's gonna be. I gotta get here my A, B, C, D, E, F, G, H, I, K, L. I want to use the notation P, M, O, P, Q, R, S, T, U, W, X, Y, Z, right? I want to use the notation of the book. Let's discover what's the Greek symbol for that. No, let's see, lowercase, it's not the one I want. A, B, C, D, E, F, A, B, C, D, F, G, H, I, L, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, it looks more like this one here. This is the C, okay? So I'm going to put here the alphabet delta chi, I think it's chi, right? Yeah, it's chi. Good. And we call it capacitive reactance. Okay. But instead of sign, you're not gonna have sign. Actually, you're gonna have a sign. It's just the argument that's gonna be different. And again, you must memorize that. We cannot derive here in this group, in this course. Is gonna be, you know, the current is going to be a little bit off phase. It's gonna be off phase by 90 degrees. And we say, I'm gonna we also say that the current leads the voltage. Okay, leads the voltage. The plus sign means that the current leads the voltage. I'm going to put voltage here side by side. Let's erase this guy. We do not need that. Okay. For the capacitor, the current, we say that the current leads the voltage. And it's the plus sign that tells whether it leads or lags. You have to memorize that. Okay. If you look at a plot, okay, of your V versus T and I versus T. Let's get this one here. I did that yesterday. Here you go. Here you go. Okay, that's the sine and sine of x plus 90. Okay. Here you go. I don't want you to look into that. Forget about that. The blue is the voltage. The orange is the current. Okay, we say again that the current leads the voltage. But remember, the leads means what? The leads comes from the positive sign that you have here. That's what happens when you plot both sine functions. Okay. The term, let's go back to the term here. The term is called the capacitive reactance. Capacitive reactance, which, by the way, which has units of resistance, which has units of resistance, ohms. Okay. So we don't talk about resistance in AC circuits. We talk about reactance in AC circuits. One more student coming in. So it's 155. Okay, those are the, there's more. Let me put a little bit here, another thing here in my table. Those tables are very useful. Okay. And phase difference plus 90 degrees. Okay. And by the way, I have to write down what this capacitive reactance is all about. You have that in your book before we go there. Here you go. The book, here you go. Resistance. Resistance doesn't change with frequency, but the capacitive reactance does change with frequency. That's an important difference between capacitors and resistors in an AC circuit. This reactance, right? This resistance, this capacitance resistance changes with the frequency. I'm going to write that down. Equals to 2 pi fc. Two pi f t. Or if you want to write down in terms of the angular frequency, omega, another way. Those two equations, we cannot derive mathematically because we need calculus, okay? Those last two equations, let's write that down here. These last two equations cannot be derived at this mathematical level. It requires calculus. The derivation requires calculus. So you must have these two equations set aside or memorize them. Either that or memorize them. Okay, leads. Current leads. Zero phase difference. You say phase in phase. In phase. Current is in phase. Let's put it this way, is in phase. Current leads voltage. I don't need that. Current is in phase with voltage. Leads voltage. We don't need that. And I'm gonna break the news here for you. For the inductor, okay? For our solenoid, doesn't have to be a solenoid, can also be a toroid. It's exactly the same equation here, but it's going to be a inductive reactance. It's a resistance associated with the inductor. Inductors, but doesn't necessarily have a resistance, but in an AC circuit, we can define an AC resistance that we call it reactance. And what's the difference? It's a minus pi over 2. Okay, phase difference is going to be minus 90 degrees. Is that easy enough to remember? Leads the voltage. Leads the voltage. And lags the voltage on the other one. Say that the current lags the voltage. We're going to elaborate that a little bit more. But now I want to take attendance. Okay, see, negative, positive, lags has nothing to do with that graph that you saw. Lags means that you have a negative sign here. Leads means that I have a positive sign here. That's what it means. Okay. Now let's go take attendance now. P07 roster. Lecture attendance. We had the Dexon. Insert here. That's 24, 23. Randy Bautista, are you there?
Yeah, I'm here, Professor. Good morning.
Okay. So, by the way, today I wake up very early here. 6 o'clock. I had to do that because today I got married. After 59 years, I finally got married. So today is a big day for me. I want to share that with you all.
Congratulations,
Hey,
Professor.
You're giving me hope, Professor. You're giving me hope.
What do you say?
I said you're giving me hope.
Hope? Why is that? You're not married yet?
Nah, I'm like 61.
61 you are?
Yeah, just starting life,
Oh, I see. Okay. Good. Thank you. I thought I was gonna die single, but I ended up getting married. So, okay, Vanessa, are you there? Thank you for all the congratulations from you. Thank you, thank you. Vanessa, no, Vanessa is here. Vanessa Bonilla, I see Vanessa here. Hi, Vanessa, I'm gonna put a star here in your name, okay?
She's in
Ashley,
the
are you
chat,
there?
Professor.
Is that Vanessa?
She's in the chat.
Is in the chat, let me see. Ah, okay, good, I saw it. Thank you, Vanessa. Next is Ashley. Ashley is not here. Okay. Natalie Espinosa. Good, thank you, Natalie. Janet Garcia. Thank you, Nur Hassan. Thank you, Nur. Blanca Hernandez.
Here.
Thank you. Kelly Hernandez. Kaylee. I don't see Kaylee here in my list. Joshua Jimenez. Joshua, I don't see Joshua either. And by the way, did you figure out when do you want the exam, the third exam? You know, do you want to remember that option I gave to you, right? We can have the exam either here or here. Okay, let me know which one you think is better. Okay, the May 22nd or May 29th, or we can leave on the 17th too. Okay, it's up to you folks. Okay. Now, next, Alondra, are you there?
I'm present, Professor, and congratulations as well.
Oh, thank you. Kennedy,
I'm here.
thank you all for the congratulations.
And I think it would be
So-
good to keep the exam where it is, so we have more time to see where our weaknesses are to
Huh?
strengthen up before the final exam.
You mean you want to keep it on the 17th for now, or is that what you meant?
Yeah, that's my vote.
That's fine. Okay. Yeah, think about that. It's okay to do either the 22nd or the 29th. Okay. And Daisy, yeah, we have time. We have time to talk about that, right? We can have time to decide. And Daisy is here. Thank you, Daisy. Yesenia Montes Rodriguez. Thank you, Ryan Ong. I see Ryan here. Okay. Arthur Pacheco. Thank you, Lady Lud. I see Lady Lud here in my list. Attendance list. Okay, but I don't hear her answering. I'll put a star here. Donia, are you there?
Here.
Thank you, Elika.
Here.
Thank you, Brianna Valencia. Okay, thank you, Brianna. Justena Youssef. Hello, Justena. Okay, thank you, Justena, right? Okay, so it's 12, that's 12, is let me adjust my date here. It's 10:05, okay, and break from 10:05 to 10:20. Okay. And I see you in 15 minutes.
Professor, I think I missed the roll attendance because my
Okay.
mic didn't work well, so I have to send a message in the chat.
Okay, label it.
Yes.
Okay, thank you. So let's see. 17 and good. So let's go. That's what we did here, okay? Okay, so now we are gonna go, let's move this one down, right? So it doesn't stay here all the time. So that's the plot, right? That's the plot of the voltage and the current for the capacitor, okay? That's what happens to the current whenever, not just to the current, but to any sine wave whenever you sum an angle in the argument, okay? It shifts to the left, okay? Notice that it's shifted to the left. It's not shifted to the right, but we still say that it leads. We say that the current leads the voltage. We still say that. And now going back here to this one. Okay, so here we go. My capacitor, right? Let's play the movie, right? Let's play the movie. Here you go. I have, okay, so the capacitor keep on charging. Now it is going to uncharge. Okay. Uncharge, uncharge, and uncharge. And now, go this way. Well, and capacitor go charge in the other direction. That's how it happens. And how does it look like in the phase diagram? In the phasor diagram, right? How it looks like in the phasor diagram. In the phasor diagram, it looks just like we said, right? The current leads the voltage by 90 degrees. That's how I mean by leads. That's another way of visualizing the current leading the voltage. And we are going to take to adjust here this one, okay? When they two are not here, when they two are together, okay, that shouldn't be omega t, that should be omega t plus 90 degrees, okay? That's omega t, and that's omega t plus 90 degrees. Omega t, this angle, I'm going to put a 90-degree angle here. I'm going to put a 90-degree angle here for you. So fill, no fill, and black, I'm going to make it, okay, thicker. This one, don't forget that this guy here is I naught. I naught is the length of the arrow. What is projected here in the y-axis is going to be the actual current at that very moment. Okay. So there, they are coupled to each other. It's better if we do like that. I wish I could. I think I can. Yeah, let's see if I can animate it. Let's see if we can animate it here. Okay, I'm gonna put this one. Oh, V not. Okay, it goes. Yeah. Let's see if I can animate that. Group. And I suspect that I cannot know. Format. Shape. Rotation. Let's see. Let's see if I can rotate it. Yeah, I can, but it's not the right axis, unfortunately. I want to rotate here about this axis, but unfortunately, it's not rotating the proper axis. I wonder how we can choose the axis where it rotates. See that? We rotate, but they are using the wrong axis, unfortunately. Yeah, there must be a way to keep this guy in the proper position while it rotates. If you discover that, let me know. Horizontal position, vertical position, top corner, top left corner. Yeah, that's the top left corner. Yeah, he must be rotating from somewhere. Maybe it's this one. Maybe that's the one they use as a rotation. Let's take a look. Yeah, must be the middle. Well, we cannot say. We cannot say. Yeah. Going back here. Okay. But there are softwares out there that you can see this type of thing being animated, right? Just like here go. When I can. Okay, like that. Now I put two, and then I can move my omega t, right? And now I have 2 frames of my movie. I'm doing that manually. Ideally, we should be doing that in an automated fashion so you don't spend as much time. And you go, rotate a little bit more. All right. Ideally, this guy here should be, yeah, the V naught too. That's unfortunate that the V naught is becoming all, here you go, V naught, I naught, yeah, and so on. This one too moves all the way down up here. Okay. And by the way, because I just want to, to mention that because there is, yeah, it's here. Ideally, I should be putting more positives and negatives here too, right? And so on. This type of fun thing that we do in our spare time. Now, what else? There is the other one, which is here's the resistor, here's the capacitor, and here is the inductance. And I'm going to get the other one too. The inductance is represented by a solenoid, the drawing of a solenoid. Let me stretch this guy a little bit so it's connected to the whole circuit. And can I move a little bit higher? Yeah, good. Okay, like that. And then we have the phasor diagram also for the inductor. Those two, here you go. Right? The voltage doesn't change for all those three. Because we are talking about, well, it's not exactly the voltage doesn't change. I'm going to explain it a little bit better. And here, my current is going to be rotated. It's going to be lagging, right? The voltage by 90 degrees. And I can rotate by, let's see, 180. Yeah, I got it right. And this guy goes all the way down here. And instead of right, minus 90, even better. Let's see if I can do this way. No, I cannot do this way. I have to do the other way. Okay, I gotta do this way. Here you go. Minus 90 degrees. Minus is going to be the clockwise direction. Like, nope. Yeah, better now. Clockwise direction and my phasor diagram. Like that. Oh, unfortunately, okay. That's they're again coupled and they rotating together with each other as though they were a rigid body. Remember, this is a mathematical representation. And we already wrote that down before, right? Here you go. 2 pi ft minus pi over 2. Lags the voltage, leads the voltage, is in phase with the voltage. Can you memorize that? What else do you have to know? Here you go. I'm going to V is going to be the same for the, and then I'm going to do the following. I'm going to emphasize that this is the current for the resistor. This is the current for the capacitor. This is the current for the inductor. So let's emphasize that. And we are going to have a different reactance for the inductor. It's not the same value, okay? Not the same value. Again, we can derive that using calculus, and here your only way to find that out is to either memorize or check the notes, right? The tables. What you have to remember, note that in this case for the capacitance is the inverse of 2 pi fc, okay? For the inductance is the inverse too, and it's not the inverse, it's the proportionality omega L. Simple enough to remember. What lags, the reactance is directly proportional to the frequency. What leads the reactance is inversely proportional. Let's put here reactance. The reactance, R, right? And for is 2 pi, I'm going to put that like that. I can even come up with reactance of the resistance, right? We don't say that, but it doesn't hurt. Right like that. And then for the capacitance, we have the inverse. Like that, and I have to change this symbol. I have to see. Easy. And I need to adjust the size of those reactants. Good. Oh, we must have a negative sign here. Formula representation, phasor representation. Phasor representation. Nope, not this one. We want another one. Want this one here. Here, phasor representation. Let's put our right angle there too. I think here, 90-degree angle. So inductive reactance increases. Resistance reactance, right? We can say is constant with the frequency. The resistance doesn't change with the frequency. The resistance associated with the capacitor, which is the capacitive reactance, decreases in a hyperbolic fashion when the inversely proportional to the frequency, and the resistance associated with this inductor, or this capacitance, let's see. Let's see. Here you go. Increases linearly with that. 2 pi f. So the larger the inductance, the larger is going to be the resistance associated with the inductor. Okay. Well, the plots look just like that. You can do the plotting yourself as well, just like I did. Instead of having a positive here, you can have a negative here, and I change everything for, don't forget, this one is for the current, this one is for the voltage, right? So when we change the phase, we say that the current lags the voltage, and that's how it looks like in a plot. V versus T, I versus T for the inductor. Is that how it looks like? Yeah, this is exactly how it looks like. Okay. We plot one, yeah, we plot more than one and a half terms here in the blue book. Okay. Okay, here we go. Okay, so we have an interesting problem here. Think about that. Okay, we have three different types of circuit. Just an AC circuit with a resistor, an AC circuit with a capacitor, an AC circuit with the inductor. We're going to put them side by side. And he's asking, he said, the frequency of each AC generator is reduced on half its initial value. Which circuit is experience the greatest increase in the current, the least change in current. Okay, all you have to do here is to go back to those. All you have to do is to go back to those equations for the current. Okay. Let's see. And I'm gonna go back here. I'm gonna put them. Oh, we have them already side by side. Okay, go. The frequency increases. What happens to the maximum value of the current? Does it change at all? Right? This is a constant and this is a constant. But what about here? I'm gonna even make it easier for you to see that because we have, I'm gonna put the current. Oh, here you go. The larger the reactance, right? The lower the current. If you increase the frequency, what's going to happen to this reactance? It's going to decrease. If this reactance decrease, this current is going to increase. Okay? But the greatest increase in the current is going to be the capacitor. It's going to be the circuit that has a capacitor in there. What's going to the least change in the current? Here, the current doesn't change at all. The current doesn't change at all. What do you mean by the current? It's actually the maximum value of the current. The current doesn't change at all. The maximum current doesn't change at all. And here, it's going to change. But it's going to decrease because the reactance, and I'm going to here write that equation in another format so you can see what I mean about the increase. Oh, you got increase and decrease. Put that here. I'm going to directly proportional to the frequency inversely proportional to the frequency. That's because the reactance is downstairs. And give them a little bit more of room here. Oops. A little bit more of room here. More, my goodness, I'm gonna need more room here. Here you go. I have it. So it's easier to see the increase of the current, but by looking at this formula. Here the current increases the frequency, here the current decreases with the frequency. Now, what about when you put everything together in a single circuit and with the resistor, the capacitor, and the inductor in series? Something interesting happens. Okay? We're going to do the RLC or the RCL, right? There is a very nice treatment on how a phasor treatment whenever we have all those elements put in the same circuit. Okay, and now instead of just this one here, I am going to have all of them together, you know, resistance, plus capacitance, plus inductance. RCL according to the book, or RLC according to other books. See, according to other books. Okay, I'm going to extend this guy a little bit more so I can fit more elements in my circuit. This way. It doesn't matter which order I put my elements. It can be R from the left to RLC from the left to the right. It can be CLR from the left to the right, or whatever combination you want. I'm going to get my symbol for the capacitor. You're going to get the resistor. Don't forget, this is a circuit in series. Like that. I don't need that. Yeah, I need that. Leave that here. RLC circuit. RL. Circuit. Okay. The resistor, inductor, and capacitor in series with a generator or AC source. A resistor, inductor, and capacitor in series with a generator. Okay. Now, there is a little trick here to understand this circuit. Okay. Because all the, and that's a very important, elements are in series, the current passing through each element will have the same phase. Okay. So now we have to, because of that, now we have to change our notation. That's the little trick that sometimes is difficult to see. Remember that the current is just flowing through this circuit, no matter it's bouncing back and forth or bouncing, whether it's bouncing back and forth or not. Okay. And because all those elements are in series, you cannot have different phases for the current flowing through each element. Otherwise, you are not going to have a continuity on the current. Okay? So we're going to put that down here. We're going to write that down. Same phase. Right? We are attempting, why I'm saying that? Because we are attempting to write down the current, just the current from the resistor as something like that has no continuity. In reality, the current in the RLC circuit has to be continuous because those elements are in series. Okay, so the current of the circuit, the current of the circuit RLC will be written as, I'm even going to, I'm going to put RLC here, so you know that you have all those three elements. Is going to be, I am not going to be V0 divided by R. I'm going to put a proportionality parameter here, and then we are going to discover what's going to be that proportion, what's going to be that parameter that goes in front of. I'll put the proportionality, here you go, proportionality right in here. That's very important. But I do know that it has to be a V0. It has to be a V0 because every term here has a V0. See that? Every term here has a V0. The key now is what goes below the V0. What's that going to go below the V0? Okay. Note, see, for every, every parameter that you see here, they do obey Ohm's law, but they obey a different Ohm's law. They obey an Ohm's law that involves the reactance, right? They obey the Ohm's law that involves the inductance. So it's not that difficult to memorize. Consequently, we must have a reactance here as well. The question is, and they usually represent this reactance. Yeah, as a Z. Let me check. The book does that, right? Let's see what they do. I want to maintain, I want to ensure that we get the oh yeah, Z, okay? Z. And let's discover what the Z is. It's also reactance. And now we can write that down as an equality. They all have this relation. V0 divided by the reactance. I wish my table had enough space. If they had enough space, I would put the RLC here as well. The question is, what's the Z? And it doesn't have to be bold-faced. This Z here, we discover by using the phasor diagram. The value of the Z reactance is found by using the phasor diagram. And what's the trick for that? Let's take a look. If the current doesn't change, the phase of the current doesn't change for each element, something else has to give in, okay? If the current in the RLC circuit does not change, comma, something else must give in, okay? Recall that the current leads right in a circuit with a capacitor and lagged in a circuit with an inductor. If in the RLC circuit, the current must be the same across all elements, it means that the voltage must make up by the voltage across each element must make up by the lagging and leading of the circuit. Okay? So let's go one by one. For the resistor, the current and the voltage are in phase. Consequently, the voltage across the resistor is not going to change. It's going to be what we had before. Okay? V for the resistor is going to be V naught. V naught sine 2 pi ft. For the capacitor, the current leads the voltage. Consequently, if we keep consequently, you go, the voltage must lag, you go, lag the current. Make sense? Or for the case of the capacitor, we must have the pi over 2 here. That's an RLC circuit. Okay, going back to our table here. See, the current leads. Consequently, the current must, the voltage must lag in an RLC circuit. And the same thing happens with for the inductor. The current lags the voltage. Consequently, the voltage must lead the current. And here is the L. Oh. So now, right, RLC, let's see if I can get everything here for this RLC now, right? RLC, I'm going to put, oops. I'm trying to find here. Let's see. Looks like I'm looking the wrong place. See, not here. No, it doesn't here. Layout must be in layout, what I want. Man. No, it's not. It must be here. I'm trying to come up with this guy. Let's see if I can do that. Delete merge. Okay, the other ones. Even better, even easier. RCL or RLC. RLC voltage doesn't change. Voltage for the capacitor is going to lead. Lead now, it's going to lag. Current leads, voltage lags. Right? Current lags, voltage leads for the inductor. And now all those currents, they must be the same because all the elements are connected in series. Okay? Phase difference minus 9, phase difference for the voltage, right? Oh, phase difference for the current is 2 plus, oh, it's 2 plus 90. It's 2 plus 90. I'm not going to change that. The current is still leading. The current here is still lagging because the voltage has this positive sign. Okay, using phase, lead, current. Okay, I don't need to change any of that. And now, do you understand why we're doing that? All those currents, even though I'm putting them in the different notation, they end up being the same, exactly the same, because all those elements are connected in series. Okay, Iga. Okay, and it's just the reactance that I spelled out, right? Oh, wait a minute, here should be different, right? Shouldn't be Z, shouldn't be R, it should be that factor Z. Okay, even better. Okay, here's going to be that factor Z that we didn't find yet. It's going to be that reactance that we didn't find yet. And yeah, that we don't need that anymore. We do not need that anymore. Because the current must be the same, they must all have the same reactance here. But how do we find this factor? How do we find this new reactance? Okay, well, there's a reason why I introduced you to the phasor diagram, right? There's a reason why I introduced you to the phasor diagram. Let's see. The current is going to be, it's not going to change the phase for the RL phasor diagram for the RLC circuit. RLC circuit. I put the delta V larger there, right? Yeah, let's put the delta, let's keep the same notation. My voltage, I'm gonna send it to the back. Yeah. Displace it a little bit more. Maybe I should make it a little bit thicker so you can see that there is something there behind, right? Better now? And I'm going to start mounting my new phasor diagram. Remember, I go. I don't need that. First, just the current. And I'm going to put the I naught. I naught. I naught here. Make a little bit thicker. Yeah, better to see him before. I will replace that one by this one, thicker. And now I'm going to add the voltage, the other voltages, right? The other voltage that I have to add is going to be the voltage of the capacitor. If the current of the capacitor leads the voltage, it means that the voltage of the capacitor lags the current. Let's get this guy rotated. No, 270. Good. Huh. Oh man, this guy doesn't want to be selected, huh? V of the capacitor. V of the capacitor. Should I put in a different color? Yeah, I should put in a different color. So you can distinguish from. Okay. And if the current of the inductor lags, it means that the voltage of the inductor, the current of the inductor lags the voltage. Right? It means that the voltage of the inductor must lead. Must lead the current. The voltage of the inductor must lead. And, you know, it doesn't have necessarily the same amplitude. Let's see if I can decrease this guy here. Oh gosh, I can't. Jesus. Let me see if I can increase. It would be better if I change. And I'm going to do it exactly according to the book, so there is no confusion, right? So in this case, the capacitor has a smaller amplitude than the voltage of the inductor. Let's see if I can get that. No solid size. Rotation. So format must be here. Height. Okay, let's see if I can do twice. No. Rotation, scale height. Ah. I'm gonna do like that. Oh no. Copy and paste. I'm gonna do all over again. I'm gonna shorten this guy. Size. Height. Width. Seven times 721. Put here 0.721. There's more to do is how you use this softer than how I 1.13, you know, than physics itself. Okay, so now I manage, and now I'm going to rotate it. Nope, nope, it's supposed to be 90. Yeah, here you go. Now I got it, what I want. This guy goes here. When you rotate that, it doesn't behave the way you want it. That's why I'm struggling here. Good, I don't need that. Good, and I'm going to change. Good. That's the capacitance. And I'll get this guy as well. I'm starting from scratch. That's what I'm doing. And then I'm going to double it. 206. 206. The other is 0.06 324. No, 324. 324, like that. Okay, and now I have to rotate. Nope, has to be 270. Yeah. There's a reason that I'm going through this trouble. It's better to go through this trouble than go through this, the other trouble of deriving everything with sine functions. I'm going to change the color of that. This one, blue. This different blue. This different blue, okay? I'm going to stretch this guy. Okay. And then what do we do next? We sum all those vectors of the V vectorially. We sum all those phasors, which behave like vectors. You know, we sum them vectorially. That's what they do. I'm gonna even do it. Here you go. Gonna do some. Here's for the resistor. Here's for the current. Here's for the resistor. Here is going to be just for the capacitor. Okay. Here is going to be just for the inductor. Okay. And now here's going to be their combination, their vectorial combination. I'm going to go the next step. Their vectorial combination, you have to subtract the vector, you know, of the capacitor from the inductor. You see that? That should be what the book calls VL minus VC. VL minus VC. I'm going to put it under a different color because now it's a different vector. Let's do that green. Oops, didn't do green here. Let's do that green again. Yeah. And now we are left to combining the phasor of the resistor with the phasor of those two. Okay. And what we end up getting. Okay, we end up getting something like that. And I'm going to come up with a different color. Let's see which color. Orange, maybe. Hopefully, orange is not gonna be that bad. No, I'm gonna use this one. It's better. Okay. Okay, so here we go. Don't need that, don't need that. And this guy is still rotating omega t, just like the current. This one now is going to be not minus, but it's going to be plus VL. Okay. And now you have to find this length here. You have to find this length here. It's not difficult. Why it's not difficult? It's not difficult because all those vectors, they are perpendicular to each other. Okay. I'm going to do that. Go. The VLC, this one here. Let's call here the VLC. The vector VLC. Subscript. Right. Let's call that the VLC. And now this one is also going to be the VLC. And now this one here, remember the VLC is perpendicular to the VR. Consequently, the magnitude of the resulting vector is going to be the square of this one plus the square of this one square root. Okay, so I'm not even going to call like that. I'm going to put RLC. Let's put VRLC, RLC, which is the Z that I named before. It's better notation. VRLC. Okay. And I can do that in the next slide. In the next slide, now in my notes. Z. This guy here is going to be my V L R L C, right? RLC, yeah. That's going to be BL minus BC okay, plus BR squared. And by the way, there is a missing square root right here. Okay. I'm using a slightly different notation, okay? Don't forget that we can come up with that Ohm's law notation, right? I'm going to put here the reactance let's see, this guy here is going to be reactance, inductive reactance. All right. Inductive capacitive reactance. I. And that's going to be my resistance. It's going to be the I as well. Okay. And the I. Here, oh, gotta be square, right? Don't forget. Here it must be square because the VR is squared. When I take out those two i's from inside the parenthesis, which by the way is being squared, the I is also squared outside. And now that we have an I square inside the root, I can take the I square inside the root and put the I outside the root. Okay, let's see. This guy here is supposed to be the I. I'm sorry, folks. You know what? That's not right here, okay? Let me erase this one. Everything else is correct. Everything else is correct. What goes here is this one, okay? Again, apply Ohm's law for this one. What we end up getting? We end up getting that reactance, the overall reactance Z. And from this equation, we discover that the net reactance of the RLC circuit is equal to this square root. Okay. And now I can, oh, what I did, here you go. I can finally use the Z right here in my equation for the current. Okay. And I will put net reactance, or I'll call that net reactance. Z equal to merge equal to that. Okay. What time is that? Oh, 11:20 already. Yeah? Man, I need a break. You must need a break too, right? It's a really neat procedure. This technique of the phasor technique is a really neat technique. Okay. It simplifies a lot the calculation that you have to do with sines and cosines. We're going to have our break now, 11:25, and break 11:25 to 11:40 a.m. And I see you shortly. Good. We are not done yet. We are not done yet. And we have to do one more sync. Okay. So what we have to do here? Okay, we have to look. I'm gonna repeat this little one here so you can understand, okay, what I'm talking about, right? So we have okay. I'm even gonna put dashed here so you understand it's just a, here you go. And it's gonna be dashed as well. Okay, and now we have this vector, and that's the resulting vector. We found the lengths of this vector. From the length of this vector, we found the net reactance. Okay. We found the net reactance. And now what else do we need to find? We need to find this angle here. Okay. We need to find this angle here between the net voltage and the current. That's what we need to do. I'll call this angle the phi angle. And that's what the book did as well. Go. I'm gonna move my I naught here. And I'm gonna call. Oh. This angle there. Oh, what happened? Yeah, here you go, phi angle. The same angle that's used in the book. Okay. And that this angle is easy to find. Okay, well, I'm gonna get this guy. Let's see. Yeah, let's leave this way. I'll put it here. I'll put it here. What I'm gonna do this way here. I'm not gonna show the phi because we're just trying to find the net voltage. Okay. From the net voltage, we find what is the total reactance. And what's going to be this angle? Okay, this angle can be easily determined by looking at, remember, we have a right angle triangle here, right? This angle can be easily determined because we know the lengths of this vector and the lengths of this vector. And let's go. Let's put that together. What is the phase of the net voltage? VRLC. Okay. Okay, that's going to be given by the tangent of phi that is, oh, not this one here, VL minus VC, okay, divided by VR. But let's not forget again our Ohm's law, right? For those quantities, I chi L, I chi C, right? And I R. I cancels out. And we are left with the reactance altogether. For the case of the inductor, it is pi 2 pi f. For the case 2 pi fl, right? For the case of the capacitance is 1 over 2 pi f times c. Is that what it is? Going back here. Yeah. Can you do better than that? Yeah, can leave this way for now. Okay. Okay. $11.48. Now we can start talking about the power. Okay, remember the relation for the power. Relation for the power, you know, for DC circuits is VI. Okay, which can also be written in terms of V equal to RI, right? So it becomes VRI square. And then there is this other relation too that we can here write. You know, V, all right, so RI. So it's V divided by R. No, 3 different relations that we know for the power. V square over R. Okay. But you know what? We're going to look at this relation here. We're going to, and now because that's for, here you go, for DC circuits. For DC circuits. Okay. For AC circuits, we have something different. It's going to be, you know, the average power. We're talking about here the average. Remember, the power in this case for AC circuits changes in time, right? The power for AC circuits changes in time because the current and voltages are a function of time, are a function of time as well. So what we must do, we must for AC circuits, here you go, I'm gonna put this way, the power changes in time because the current voltage are a function of time as well. For this reason, we must calculate an average power. And the average power is going to be represented by that bar that goes at the top of the letter. That's the notation of your book as well. Bar, here you go. And I can either use this guy or I can use this guy, okay? The resistance for an AC circuit is in reality your reactance, right? So we have to replace, but there's another detail here. And the current is going to be a root mean square current. And there is one important detail here. It's going to be the voltage along the direction of the current. Not this one, the other one. The voltage along the direction of the current is not going to be the full voltage here. And I'm going to, you know, VRL. I'm going to label that to the voltage along the direction of the current is going to be this guy here times cosine of phi. Okay, so we have to include the cosine of phi in this equation. And I'm going to keep it in the form of the book. Okay. What else can I do? I can here write that just like the book did, you know. I can break down this I into i's. Go to the square, another one. Oh, I didn't do the right way. Right, C, RMS, R, RMS. Right, like that. What you have here is going to be your V. I don't need this guy. Take it out. Okay, V go RI. Okay, that's what we have here. Is 11:55 now. Let's see if we have time to do something else. Now, voltage and power in RCL, RLC. Okay, depends on which book we are talking about. Yeah, okay, so let's just go quickly. There's some interesting applications here in this book. So, you know, how can you apply that? When you apply that, one of the applications of this type of theory is on body fat scans. All those scales that can calculate your fat percentage, right? And it uses the impedance of an AC circuit. Okay, that's what it does. It passes a current, an AC current through you. You step there in the electrodes. It passes a current through your whole body, very small current that you don't feel, and you obtain the impedance throughout your body. The current is an AC current, by the way. Okay, electrodes for the heel, electrodes for the balls of feet. Okay, and it's a very complex circuit. As an example of a very complex circuit, consider the human body. Okay, it contains muscle, which is relatively good conductor of electricity due to its high water content, and also fat, with a relatively poor conductor due to its low water content. The impedance that the body offers to an AC electricity is referred to a bioelectrical impedance and is largely determined by resistance and capacitive reactance. Capacitance enters the picture because cell membranes can act like tiny capacitors. Remember that I told you that some cells behave like capacitors because they can have you know, ions outside and inside the cell. Bioelectric impedance analysis provides the basis for the determination of body fat percentage by the body fat scale. This one, that are widely available for home use. When you stand barefoot on such a scale, electrodes beneath your feet send a weak AC current, 800 microamps amplitude with a frequency of 50 kilohertz, 50,000 hertz, through your lower body in order to measure body's impedance. The scale also measures your weight. A built-in computer combines the impedance and weight with information you provide about your height, age, and sex to determine the percentage fat in your body to an accuracy of about 5%, okay? For men age 20 to 39, a percentage of 8 to 19 is considered average. Okay, so here is telling you how those devices work. And here we have, I want you to look by yourself on those conceptual examples, okay? They are important. Here is all the material that we covered, some other examples, numerical examples here. 1158. Okay, and current in series RCL circuit. Okay, don't forget, you can also have RC circuit and RL circuit. Don't forget that. We didn't do that because everything that we did, you know, is kind of straightforward transferred to the RC, RL, and CL circuits. And we have those examples. Oh, that's another application, transcutaneous electrical nerve stimulation. Okay. And I'm not going to cover 23.4 and 23.5 later on. If we need, I come back to it. Okay, this one we may need to cover later on, but for now we're done with this. Oh, here you go. Here's the semiconductor devices. Okay, we're not covering the same. Semiconductor devices are advanced devices. Transistors is a type of semiconductor device. And we're not covering that, and that's, like I said, for more advanced course. And I guess that's all you have. Any questions about that? Chapter 23, okay? 23, 1, 2, and 3, 4, and 5 we're not covering, at least now. Chapters, we're skipping chapters, sections 23.4 and 5, right? Let's go back there. Yeah. For now. The 5 definitely, the 4 maybe. Okay, for now. next time. So we are going to get into electromagnetic radiation, electromagnetic waves. Okay. And if you don't have any questions, we can stop here, and I have office hours right now. See you again on Wednesday.
Thank you, Professor. Enjoy the rest of your wedding day.
Thank you.